Hello everyone. In this video lecture we are going to discuss about designing the controllers for the non-minimum phase systems using the frequency response of the systems using the body plot. In the next video lecture we will focus on the transport delay. So for now we will check the non-minimum phase systems. Basically a non-minimum phase system is a system which has a zero or one or more zeros on the right half plane. So right half plane zeros. The systems that we have been considering till now, they never had zeros on the right half plane. So all the zeros and also the poles of the systems that we have discussed till now were lying on the left half plane. For the non-minimum phase systems, however, we might have, or we will have indeed, zeros on the right half plane. But all the poles should be on the left half plane because that's one of the requirements for designing the controller using this approach. We need to have our open loop system stable. So for the non-minimum phase systems, we will have right half plane zeros. And this right half plane zeros will make designing the controller more difficult than what we have for the minimum phase systems. Because you know that when a zero is on the right half plane, in terms of the phase, its phase will become negative. So let me maybe show you here how a zero which is on the right half plane will behave in terms of the phase compared to a one which is on the left half plane. So let's say here we have z1 and we have the second zero, both of them at the same frequency, one on the right side and one on the left side. Here we have, let's say, at 1 and -1. In terms of the amplitude, for both of them we will have the same amplitude graph. So with 20 decibel per decade in terms of the slope of that part of the body plot. But then in terms of the phase, you can see that for the zero which is on the left side, for Z2, the phase will start from 0, it will become plus pi over 4, and eventually it will reach plus pi over 2. So this will be the phase diagram for the 0 on the left half plane. This is for Z2. But when the 0 is on the right half plane, its angle or phase will become negative. It will behave like a pole indeed. This is what we have for Z1. And you can just find out why this happens by referring to the formulation that we have for the 0. So for the 0, we'll have it in the form of S plus Z, or we can write it in the form of Z1 or Z2, let's say. In order to obtain the angle, we replace S with j omega, so we'll have j omega plus Z1, and then the phase of j omega plus Z1 will be obtained as the inverse tangent of omega over Z1. Now, if Z1 is positive, when Z1 is bigger than 0, meaning that we have the pole on the left half plane, or our system is minimum phase, then this inverse tangent of omega over Z1 will be bigger than 0, generally. But when Z1 is smaller than 0, meaning that we have the 0, this is 0, we have the 0 on the right half plane, and we have a non-minimum phase system, then the inverse tangent of omega over Z1 will be smaller than 0. So this is what we have for non-minimum phase systems. So the phase of the system will get bigger and bigger towards the negative values. And this will make designing the controller more difficult. Let's see here through an example how this happens. So here we have the system, the plant, given in the form of 0.1 times 1 minus 2s over s times 1 plus 10s times 1 plus 0.1s. This is indeed the transfer function that we have for a part of the airplane. This is the transfer function between the angle of the elevators, delta E of an airplane, and the airplane altitude h of t. We had this in past year. We have considered the example already. So you can see that here we have a 0 at s equal to plus 1 over 2 or 0.5. So we have a non-minimum phase system. We need to design a controller for this system by designing the body diagram of L such that the controller is at most indeed it's a proportional one or it's a first order controller, okay? So we don't go beyond first order controllers. We need to have the steady state error equal to 0 for the step in reference input, and we can see that it is already satisfied because we have a type 1 system here. We need to have the phase margin at least 45 degrees and the crossover frequency omega c as large as possible, while we satisfy all the other requirements. Okay, so we can start by plotting the body diagram for the system. Over here, you can see the body plot for the non-minimum phase system that we have and we are considering. And also the body diagram for a minimum phase system with the poles and zeros at the same location, but the 0 is on the left half plane now. So indeed what we have, the transfer function that we have for G bar, I will call it, we'll have the 0 on the left half plane. It will be equal to 0.1 times 1 plus 2s. 1 plus 2s, and at the denominator we have the same terms. You can see that in terms of the amplitude, both of them are the same, so we have the same amplitude. But in terms of the phase, you can see what happens when we have a 0 on the left half plane. If we move the 0 from left side to the right side, you see that a huge amount of negative phase will be introduced. At the end, we will have, instead of having minus 180, we'll go down to minus 360. So we have minus 180 degrees less indeed, for the non-minimum phase system. If you consider the absolute value, you can see why this is called the minimum phase system, because its phase is smaller than the non-minimum phase system. So you see that at the point in which a 0 is located on the right half plane at omega equal to 0.5, which is this frequency. At that frequency, the slope that we have for the phase and where the phase goes down gets worse, indeed. While if we had it, and of course it starts from the previous, from smaller, let's say, values for the frequency, because we see the effect of the 0 even earlier. So now you can see that, if you compare the non-minimum phase system and the minimum phase system with each other, since the phase that we have for the non-minimum phase system is kind of reaching minus 180 degrees earlier, it will be more difficult to find the controller, a compensator, in order to satisfy the requirements. The system will become quickly unstable if we try to increase the crossover frequency. So having that in mind, let's see how we are going to deal with this. So we have a type 1 system, static requirement is satisfied. We can eventually use a proportional controller to have omega c being equal to 0.1 radian per second, which is achievable by gc of s equal to 1, but we can't go beyond that. If we try to increase the crossover frequency by using a proportional controller and moving the amplitude plot upwards, the crossover frequency will increase, but at the same time we will quickly the system will become, at some point it will become unstable. But before that, we will not satisfy the requirement on the phase margin. If we go beyond this value, the phase margin will become smaller than 45 degrees. And the requirement is to have it at least 45 degrees. This means that using a proportional controller, we cannot increase the crossover frequency and have the phase margin as desired. Another option would be to increase omega C by using a lead compensator. So we use the lead compensator. We know that by using that, the amplitude plot at high frequencies will move upwards. As a result, the crossover frequency will increase, and we will also inject some positive phase into the system. And therefore, the phase margin could be increased at the same time that we have the crossover frequency being increased. To design the phase lead compensator, we need to pick two values, omega m and phi m. For omega m, let's use 1 radian per second. And for phi m, let's pick a big value. Yeah? We want to increase positive phase as much as possible in order to be able to increase the crossover frequency. So if we take phi m equal to 78 degrees, with omega m equal to 1, then you can refer to the formulations that we have for the lead compensator. You will end up with alpha equal to 0.01. And eventually we will have the values for the pole and 0 of the controller. The 0 will be equal to 0.1 and the pole will be located at 10. So having these picked values that we have, with omega m equal to 1 and phi m equal to 78 degrees, we end up with a controller with ZC equal to 0.1 and PC equal to 10, and alpha is equal to 0.01. Now we can introduce that. Here we have that part of the lead compensator, 1 plus 10s over 1 plus 0.1s, and we also have a proportional gain as a free variable for now. LOS, the loop transfer function, will look like this: 0.1 times GC tilde times 1 minus 2s over s times 1 plus 0.1s. And now we can have a look at the shape of L of j omega to pick a proper value for GC tilde. And we will see that if you look here, over here, you can see what we have for the original system, where GC of S is equal to 1, and for the lead compensated system. And here we have GC tilde equal to 1. Yeah? So we can try to introduce a proportional part and increase the value for the generalized gain from 1 to some value. But you should notice that if we can do it up to some extent, yeah, because over here the part of the amplitude plot is kind of flat. So if we try to move further, there will be a jump in terms of the crossover frequency from here to here, and as a result, the system will become unstable because the phase will fall below minus 180 degrees. So we will not be able to go beyond 0.5 radian per second. And if we do so, there will be a jump in terms of the crossover frequency and the system will become unstable. Now, in order to obtain the approximate value for GC bar, we can check the current value at that frequency at 0.5. We check the value that we have over here, and then we introduce this increase in terms of the amplitude, and then we will have the crossover frequency equal to almost 0.5. You can also approximate it in this way. We just include all the singularities strictly to the left of 0.5 radian per second, and L1 of j omega will have this form. And then we want to have the amplitude of L1 equal to 1 at omega equal to 0.5. So GC tilde will be obtained as 5. This approach gives us an approximate value for GC tilde because we are kind of neglecting the components which happen at higher frequencies higher than 0.5 radian per second, because we assume that they are, in terms of the amplitude, they have 0 decibel, till that spatial frequency. So if we pick some value a little bit smaller than this GC tilde, these are GC tilde, like 4.2, we will obtain the controller in the form of 4.2 times 1 plus 10s over 1 plus 0.1s, which gives us this transfer function for L of s. And with that, we will have the crossover frequency equal to 0.42, and the phase margin will be 45.16 degrees. This is kind of the final controller that we could obtain. And over here you can see the body plot for the original system, or GC equal to 1. This is the lead compensated. And this is the last controller that we just obtained with GC tilde equal to 0.42. Now the crossover frequency is 0.42. The phase margin is 45 for the green one indeed. We have 40 around here. We have 45.16 degrees. If we try to increase the crossover frequency further, you see that we have the flat part of the amplitude plot over here. So the crossover frequency will jump from there to here. And if we are there, you see that the system will become unstable. So we are kind of limited in terms of the maximum crossover frequency that we can obtain. You can try indeed to add more higher order indeed controllers. We can have double lead compensator in order to inject positive phase here and also increase the crossover frequency, but we can't go, we not be able to do much indeed. And the maximum crossover frequency that we might get will be limited. So that's why designing the controllers for the non-minimum phase systems will be more challenging compared to the minimum phase systems. Alright, so I think that's all for this video. I hope you have learned about the non-minimum phase systems, how to deal with such systems, and how to design the controllers, and you have seen the limitations that we have in terms of the maximum achievable crossover frequency. As the phase value that we have for such systems goes quickly towards negative values, and the amplitude plot at some point becomes flat. So there will be a jump in terms of the crossover frequency if we try to increase the crossover frequency above a given value. Alright, so thank you for watching, and see you in the next video, which will be regarding the transport delay.